All right, so we're going to talk about solutions A through D of the recent Codeforces round 1036. All right, so problem A, in short, says you have an array of length n elements. Remove some set of it. Could be empty, could be full. Just remove any subset you want. The question is the remaining array a derangement? And a derangement basically means that no such element is in its correct position, or the position it would be if it was sorted in non-decreasing order. So intuitively, the first thing that should strike you is that any array that's sorted, um, no matter what subset you remove, that array will still be sorted, and therefore it's not going to be derangement because literally not only is no is not only is every element not in its incorrect position, every element is in its correct position for a sorted array. So like obviously something sorted is not a derangement; it's like the opposite of a derangement. Um, so we first know that if the array is sorted, then we're cooked. We can't form a derangement. But there's a specific definition of sorted, right? In non-decreasing order. If an array is sorted in non-decreasing order, there does not exist an index that satisfies AI. Uh, there does not. So if an array is sorted in non-decreasing order, then this is not true, right? There is no I. There's no I that does this. That means basically what this basically means that over an adjacent pair of elements, there's no elements that descend. There's no pair that descends in value. So you can have like 6 and then 5 and expect the array to be in non-decreasing order. So basically, like what this basically means is that uh, if the array is sorted, then there's no adjacent pairs that are out of order. Every adjacent pair is in order, and so that's very intuitive, right? So basically, if the array is sorted, we know that it doesn't work. But if the array is not sorted, then we can just form a derangement because what we can do is imagine we'll have at least one pair that's out of order, right? We'll have at least one pair that's out of order that descends in value, and we can remove all the elements in the front and all the elements in the back, and just have this array. And then we obviously have a derangement because we have two elements, and 6 is not in its correct position; it should be in the last spot, and 5 is not in the correct position; it should be in the first spot, and therefore, that's our solution. So what we're going to do is we're going to check, or you'll see in the code, we're going to iterate over all adjacent pairs, and then if there is an adjacent pair that's out of order, then we know that this is possible. We'll print yes in that adjacent pair. If there's no adjacent pair that's out of order, that means the array is sorted, and therefore there's no way we can form a derangement by removing some subset of elements. So we'll go into problem B. So problem B. So in this problem, you basically have an array. So let's just keep it simple: 1, 2, 3. And in one operation, you can choose some value, and this is like your a sub j, and then transfer the value a sub j onto some value a sub I, so any element that came before you, and basically add it. So we had 1 here, now we added 3, and now this is 0, and this a sub I is the sum of a sub j and the original a sub I. So 420. So I think that's pretty clear, and we're allowed at most one operation of this, and we want to minimize this value, the sum of the prefix minimums. So the way that you think about this problem is, and the actual contest had a more complicated solution than I needed to be, but you can just think about like, well, there's two ways. The first way is you can think of like fixing a j and then finding the best possible I you can uh, you can do for each j, but I think that's not the way that they want you to think about in this problem, right? This problem is, so you first think about the contribution of each element. So if you have this array A1, right, A2, and you kind of go to AN, no matter what you do, A1 will always contribute to your answer. So then you go to A2 and you're like, will A2 contribute to my answer? The only way that A2 can contribute to your answer is if A1 is greater than A2, because then the prefix minimum is A2. So then you go to A3 and you're like, well, can A3 contribute to my answer? Well, intuitively, I don't want it to contribute to my answer because right now the prefix minimum is A2. But what I could do is I could still remain this sum by doing the operation here, right? Doing the operation here, and then I would have A1 plus A2, and then I would have a 0 here, and then everything else would just contribute 0. So you don't need a contribution outside of the element 2. And so that's like the trick here, is you don't need a contribution outside the element 2, at least for this case, right? So let's look at the other case. You can just put greater than or equal to. The other case is like if A1 is less than A2. So in this case, we'll never like a2 should not contribute because it's just going to be a1 is still the prefix minimum. But the question is, in a similar vein, we might ask ourselves, well, does a3 need to contribute? Do we need to? So there, it makes no sense for a3 to contribute because what we can do is we can make this 0, right, and push this value here, and we'll have a2 plus a3, and that won't change the fact that the minimum value is still a1 considering the first two elements, because obviously if a2 is more than a1, then a2 plus a3 is still going to be more than a1, so the prefix minimum is still a1 there. So outside the value of 2, we have 0 contribution. So then, the total value is 2a1 here, and the value here is a1 plus a2. So in these cases, right, the answer would be this, and the answer would be this. In these cases, it would be, I actually, so let me write it more clearly. So in this case, we have a1 plus a1, and in the other case, so I'll write it here, we had uh, a1 plus a2. And basically what we're doing is we're just adding a1 always, and we just add the one that's smaller. So a2 is smaller here, and then a1 is smaller here. So it's really just a1 plus the minimum of a1 and a2. That's how you could write it without an if statement, obviously. It's just a1 plus the one that's smaller, as you can notice here. So yeah, in code, you could just do this too, right? That also works too. But I think yeah, that should work. So yeah, that's the solution for this problem. It just happens to be these two. But yeah, the way you think about this is you really think, like, just ask yourself, what is the contribution of each element, and you realize that you make an observation that you never need a contribution outside of 2, and then you kind of do some casework. If you know that a1 and a2 are the only elements that contribute, you do some like kind of casework, which is a little bit annoying to think about, but like that's the solution. So subset multiplication. So basically we have some array a1. I'll just do an example, right? 1, 2, 3, 4, 5, and we choose maybe like some subset to be scaled by a value x. So maybe we choose x equals 2, and I choose some subset. Then I just like multiply, the subset. Maybe let me choose them not adjacent to show that subset doesn't have to be adjacent. So maybe 2 and 4. Maybe I double their values, and then 4 and 8, right? So given this array, so we're given this array in the problem, and we have to figure out what that x was. So we know that like 4 divided by 2, then 8 divided by 2, so the x is 2 to restore it, right? So I actually kind of like this problem. This problem is pretty good. I did solve this in contest, but like uh, I think I could have solved it much cleaner if I'd sort of just kind of thought about it more. But like I still solved the problem. So the idea here is this, right? So basically you'll try some test cases. You can do that. I mean, it's important. I try to working a lot on this test case, but I should have generalized my ideas. I don't think I generalized my ideas, and that's why it took me like an hour to solve this problem. If I generalized my ideas right away, then it would have, this is more of like a math problem, so I should have just generalized my ideas. So the idea is that like you'll run into an issue, right? So, oh, I forgot to say this. There's a very important property, and it's called a beautiful array. So yeah, so there's something very important by the problem that I didn't talk about. So it's actually a beautiful array. So that means that like every element, divides the previous element. So uh, every element divides the next the successor, right? So 4 is going to divide the next element, 8 is going to divide the next element. This divides like maybe the next one. So basically, a sub I will divide a sub I plus 1, right? Will divide the successor. So yeah, that's the property, right? But then the idea is that we're supposed to like, so given the fact that like we have b, which was just like taking some subset of a and multiplying by x, and then restoring those values back, we need to figure out how to figure out what the x was. Right, yeah. So the idea was this, right? So the idea is this. So here's the idea. You need to understand that if you run into an issue, so the thing is, multiplying some subset of A will like more than likely ruin this beautiful property, right? More than likely it'll ruin this beautiful property. Now, if there are multiple possible integers, you can output any of them. So for example, if this is like 2, 4, 8, and like we like double all the values, like so this was A and then we doubled all the values, so it'd be like 4. So our subset was like we chose was just the entire thing, 816. Then technically I could put like 343 and then just choose not, like x could be 343 and then the subset that I choose is empty, which is kind of what this thing is doing over here. And that's just because like for the first test case, like 2 and 4, like like it already satisfies the property, right? So like if it already satisfies the property, it's kind of ambiguous. I mean, it could be one, A could be 1, 2, but it could also very well just be 2, 4, and we just didn't change anything with the value we had for x. So x could be anything that it wants. So the idea here is that like we only care about adjacent pairs that ruin the fact that the about this property, right? For example, like if for all I, b of I still divides b of I plus 1, then the value we choose for x can be anything we want. So at least the first test case tells us like if b sub I divides b sub I plus I1 for all I, yes, for all I, then x could be anything that it wants to be. It doesn't matter. So that's what the first test case tells us. So this means that we want to look at a case where this is not true, right? Where b sub I does not divide b sub I. This is where we have a problem, right? X can't just be whatever it wants, right? We know that a sub I is supposed to divide a sub I plus 1, but we multiplied one of these values by x, obviously, and it ruined this property. Obviously, what's very interesting here is that like you can never multiply your subset can never include adjacent value pairs values, because um if it includes adjacent values, like you multiply both of them by x, for example. And like for example, if you have like 10 divided by 2, and this was like your 10 and this is like your 2, like if you multiply both of them by x now, like it's not going to change the fact that the bottom number still divides the top number. So obviously it's the case that if this is true, one of them was divided by x. Now if you think about it, we know that um, this is supposed to be true, right? But it's not, because when we multiplied one of them by x. So the idea is that we must basically like so one of so the idea is that one of these values we must divide by x. But we also know that in this case, if this is true for all values, then a sub I plus 1 is tr- obviously greater than a sub I, right? Now, this is like an obvious statement, right? So the idea is that we know that one of these values was divided by x. The question is which one is divided by x. It makes no sense. Like, I don't know about you, but it makes no sense to divide, to assume that the uh one on the right, like b sub I plus 1, was divided by x, right? Because because if I assume that this thing was divided by x, then it could be smaller than b sub I, and that's obviously not the case, because we know that our property is that um this is like an increasing this is like a non-decreasing array. So it makes no sense for me to have divide b sub I plus 1 over x, because then it it, not saying that this doesn't work, but like it makes no sense, because obviously uh obviously we know that like this could potentially cause b sub I plus 1 to go under b sub I, which is a problem, right? That's a problem. And that's not because we know that a sub I plus 1 should be greater than a sub I. So we know now that b sub I should be the one that divides by x, right? Like we're gonna divide this by x, and the intuition is we need this to divide this, because this is basically the values. So another thing that you can think of is we know that right now, right, that this is not an integer, but somehow after I divide this by x, it is an integer, right? Somehow after I divide this by x, it's an integer. So now let's think about it. Why was this not an integer in the first place, right? Why was this not an integer in the first place? That's what we have to ask ourselves. It wasn't an integer in the first place because outside of everything that was common to both b sub I plus b sub I, so like the common thing, right? Outside of everything that was common, there's some excess stuff here. So some excess stuff here for e. There's some excess stuff in b sub I, right? So maybe b sub I is like, you can write this as e. Outside of what was common between b sub I and b sub I plus 1 and b sub I, which is simply just the GCD. So I'll let G be the GCD of bi and bi plus 1. Outside of everything that was common to them, right? So maybe this, you can write this as like eg, and I don't know, maybe this is written as like g times f. I don't know. Outside of everything that was common to them, obviously we know that e did not divide f, right? So that was the problem. E did not divide f. Uh, so this was the reason. This excess, right? Right. This was the reason. We have this excessive stuff, right? Um, and basically, yeah, E didn't divide f, right? Because like this could be, the common stuff could be removed, but then E does not divide f, right? So that was the problem, right? That's why this thing wasn't an integer in the first place. So in order to cause this, it must be the case that that we have to divide this number by e. We have to remove the excess stuff from b sub I. We have to remove that excess stuff, right? So basically, our x, the thing that we divided b sub I by, right? It has to be not necessarily equal because there's more adjacent pairs, but we non-negotiably must have x divide e. Like x has to be some multiple of e, right? X. So we know that like x just has to has, and it tells us like we're guaranteed a working solution. So it's guaranteed that an x here exists. But the idea is that like we don't know if x is equal to e, but we non-negotiably know that x must divide e. It could divide some multiple or something, but or we could, for example, we could divide more than just from this thing. We could divide like maybe 2e or whatever. But the point is, the minimal assumption is that x must divide e. Like the minimal assumption is that x must divide e. So maybe this is like complicated, but an intuitive way to say this is like to explain this problem is that we first must think, why was this not an integer in the first place? Because the number below contained, outside of everything that was common to both numbers, it contained like that excess. Now we know that we have to divide that number by x, right? That number was divided by x. And so if that number was divided by x, you know, or like, yeah, so we know what we have to take away that excess out. Like that's the only way. So that means that x must divide e, or x must divide e, non-negotiably. So this is basically all it is, because then for every adjacent pair, you can just have like maybe like x must divide e1, x must divide e2, where these are like all the excesses. You'll have a bunch of these statements, and then you know that like your x, if x has to divide e1 then e2 all the way to en, is simply just the LCM. It's simply just the LCM of all of them, right? Like if x has to divide 2 and 3, then x has to divide 6. X has to divide, so that's how math works, right? So it's simply just the LCM of all of them. Okay. So the way that I did this in contest was not necessarily LCM. You can code your own LCM, but what I did was well, I noticed that I had to get everything that was common to them, and then the way that I get my E is I just remove it from, because this is EG, so I remove the G, and so then to get the LCM, for another thing you can do is that if you need something to divide 6 and let's say 14, you basically need it. You need it to divide 84, but then you remove the GCD between these. The GCD is like um I believe 2, so you really needed to divide 42 if you needed to divide 6 and 14. So that's what you could also do. Um, if to figure out what x is, just basically like multiply them, and then divided by the GCD of both of them, right? To like remove the thing that was common between them. That you don't need that stuff. So yeah, and then you just print out your answer for x. This is what your x is. Yeah, so that's pretty much it. So yeah, this question was pretty good. I kind of liked it. So I mean, the basic premise of this problem, I think it's, I don't know, bro. This feels like a much harder problem. I mean, I don't know. A lot of people solve this in contests though, but it's whatever. Is it? Could AI solve this? I don't know. But I mean, I think it's not too difficult. But the reason, you just have to think, right? The first element says, it tells you, the first test case actually just shows you that if there's no pair such that b sub I divides b sub I plus 1, then then x can be whatever it wants. It's only when there is a pair that we have to start worrying that we actually need an x. And then we have to think about ourselves, why was this not an integer, right? And this is where x comes in handy. Um, and we know that, like, in order to make it an integer, we have to divide that bottom by x. But you have to think about which one was like divided by x, and we already proved that the one before it should be divided by x. So yeah, those are my thoughts to those problems. So those, like, that's kind of like a stream of. So I guess an idea is just like notice things and like question is like kind of the general strategy. But I think a faster way is just thinking about this just Jason pair. I should have just generalized my solution. All right. All right. Make a palindrome. So yeah, this question is like it's funny because I thought about this. Another funny thing is, like, in Java, I'll just tell y'all, never do this because uh after values, so don't compare like two integer objects, because Java will you think that Java would wrap these to integers, but after the value of 127, it doesn't wrap it to an integer, and instead just compares the memory addresses. Or maybe it always compares the memory addresses, but like if they have the same value, they both have the same memory address. I don't know. Anyways, don't do this because that was my one line difference was, when you're comparing integer objects in Java, you just use dot equals. Like, that's how you should compare two objects. Anyways, you shouldn't use, like, this is, you never use this for comparing objects. So I guess that was my rookie mistake. But anyways, I thought it would use like auto boxing or like wrapping, whatever. Um, that's what a wrapper class I thought it would do. But I guess I don't know. I don't know. It's whatever. That's kind of dumb. But anyways, that was just for practice. So enough of me yapping about Java. So basically in this question, yeah, we have an array of elements, and basically, you know, in order to remove an element, right, from the array, so we might have like 1, 2, 2, 1, 3. In order to like remove an element from the array, like we have some k, so maybe like k is equal to 3. You must find like a subarray where, if I want to remove 2, 2 is the third smallest value, and in this case it is, right, 1, 1, 2. It's obviously the third smallest value. Yeah, that's what it means by it. It basically means that if you were to sort it, um, and like, you can remove it if it's a third, but you can also remove this, right? Because this is also, so you might say, is this the fourth smallest value? It's still, all of this is still the third smallest value, right? So you have like this is the first smallest, but technically one is also the second smallest, so it's like kind of confusing. But basically what it means is that what this means is that you'll take your subarray, do 1, 1, 2, 2, 1, 3, and basically you'll find the kth element, and anything with that value. So you'll just find the kth element. Anything with that value can be removed from your subarray, right? That's basically what this means. So once you like kind of understand the question, then we can start thinking about this. So there's one observation that honestly reveals a lot about this question, and this was not how it was explained in the editorial. But I think I like this observation because this is the observation that really made the question a lot easier. So if you think about it logically, right? In a palindrome, right? So in a palindrome, let's say I have already existing palindrome. But let's say this was actually a very long palindrome. I'm just gonna do this. So in a palindrome, if I remove all such instances of one number, so maybe it's this is still a palindrome. It does not matter, right? If I remove every single occurrence, same thing here. If I remove all the twos, still a palindrome. Doesn't matter. If I remove all the threes, still a palindrome. Doesn't matter. So if I remove every single occurrence of a number in a palindrome, it's still a palindrome. In fact, uh, sometimes I want to do that. So, for example, let's say like this one wasn't like making this a palindrome. I would want to remove all the instances of one, right? And then now I have a palindrome, right? So that's like if you remove all the instances of one number in a palindrome, you still have a palindrome. And I think it's like very intuitive, like and the idea is that because well, like these values are obviously placed by symmetry. So if you remove all the instances, you remove all the things on this side, all the things on this side in the same location. So obviously it's still going to be a palindrome, right? So because of the symmetry, right? So that's the cool thing though. Like you're like it's obvious in hindsight, but like the reason why this observation is important, and you might ask yourself, well, how would you come up with this observation? Um, because the solution doesn't really explain it like this. You can look at it is you would think to yourself, well, do I really need this seven? I don't. But I also know that the seven, it doesn't even have like just look at this test case. It doesn't even have another seven, right? And like maybe it's gonna be in the center of my palindrome, but I highly doubt that, right? So let me just get rid of this seven, right? And if there and because it's the maximum value, you can just choose any window of size k. In this case, our k is 5. You can choose any window of size 5 and just remove it. It doesn't like you know that it's gonna be the last one, which is 5, and then you get out of here. And if there's like all sevens, right, you would just keep doing that. You would just remove them as long as you can have a window of size 5 because you would remove all such instances of the max element. There's no you don't need to make this more complicated than it is. Just remove all such instances, right? Like if this if we can form a like this won't if we can form a palindrome, right? Removing all instances will only help us. It will never hurt us. So remove all instances of the max, and you can obviously just do that because as long as there's like you know as long as you can make a window of size k. So as long as you have k elements left, you can obviously remove the max element. So just remove all instances of here, and we know that the amount of elements now that we have is 7. And the same thing here, same logic. I'm just gonna say remove all the maxes. I don't even care that they're on like nice. They're nice and symmetrical. Just remove them. Simplify the problem. I don't need this stuff. I can just remove them, and there's still now there's uh 1, 2, 3, 4, 5. There's 5 elements left, and I know. But now here's the thing. Here's why you must stop, right? Because you know that you might say, well, let me remove all the instances of the max here. If I remove all the instances of the max here, after I move this one, I might like choose a subarray of length 5 to remove the 3. Now I have this 3. I can't choose a subarray of length 5 to remove it. So I'm kind of cooked, right? Because I like after you have k, if you have k minus 1 elements, you obviously can't like have a there's gonna be at least k minus 1 elements in there, right? Like obviously. Um, And so, like, obviously, like, if removing the max element, all the instances, like at some point it won't be possible, right? And then this is the point, right? We can't remove both threes. But then after this, we know that we can't remove both threes. We might look at this and say, well, okay, I can only remove one three. I can only remove one three after, and so I can't remove. Um, there's exactly 5 elements. So if I can only remove 1, 3, I might just look at the. So I might just like after I've done all those removals, I might just look at the ends of the array and check are they equal, and if they're not, then I need to remove this 3. But now I can't remove anymore. Like I'm done. I can't remove anymore. It's over. So then like I'm just stuck here, and this is obviously not a palindrome. So my answer is no. Right. So from this test case, you can actually kind of like derive that observation of like kind of removing all the instances of the max, and so basically what we know is that we're basically going to just remove all occurrences of the max, like absolutely get them out of here. And you don't have to simulate this with a multi-set. There's an easier way to do this. We'll like remove all instances of the max, right? But we have to understand that like if I want to remove all instances of the number, it must be the case that if I want to remove all instances of a number, that before I remove it, right? Before I remove it, I'm going to have at least k minus 1 elements left, right? That must be the condition. Because if I removed it, that means I removed it in at least in a subarray of length k, right? And so like if removing it gives me at least k minus 1 elements, then I can remove all instances, right? So then the thing is like so then how does this look like? So if we have our thing like sorted, right? Our array sorted in an order, right? From A1, this is like a sorted array. What we can think about is like, well, we know uh, that we need at least like uh, we need at least k elements here, right? So or k minus 1. So we might just like go here. This is like sorted in order. A sub k. So one thing is that we can just remove all instances of a sub n and whatever, remove all instances, and the question is, can we remove all instances of a sub k? The thing is, you might. So for example, let's say this is like a 1. You might have some 1s that are in here too, and so removing all instances of this would uh like it would make the remaining elements have not at least k minus 1 elements. So the question, so the idea is that like if you just remove remove all x greater than ak. If you remove all x greater than ak, all of them, right? Then we're fine. Um, so basically, like you know, remove all x greater than a sub k, and then we'll still have we know for a damn fact that we're gonna be fine, right? I will remove all those elements, and the reason I'm doing that is because I know for a fact that I can remove all those elements because it's gonna be a possible operation. Like I already showed you that you can remove all the instances of an element, right? Like the max, and then you can still have like a you can still have a palindrome. So that's basically what you do. Remove all x greater than ak. So now we've reduced this to just saying we have a bunch of elements. Some are ak and some are not. So some are ak, some are not ak. Okay, where k is like this is sorted. So some are ak and some are not ak. So let's try this on a sample to make sure we're chilling. So there's not. I didn't give us like the most interesting examples, but in this case we have 4. So could I remove all the instances of? No, there's nothing that I can remove. This is an example of maybe something that's like, there are AKs two, and then the things that are not AK is just like just one. So we're like, okay, maybe the thing is like we might just check like if we have a palindrome by like checking the left and right, and but we know that like if the ends don't agree, right? Like it also like another observation that I forgot to make is once you have this remaining element, it's absolutely like you can only like here's the thing, because a sub k is the max, right? A sub k is now the max element, right? We removed all x greater than a sub k. A sub k is now the max, so this is now the max element, right? A sub k is now the max element. Then this is the only element that we can, like, for example, we can't remove all instances of a sub k. We can only remove some of a sub k. So now we know that we can only remove some of a sub k. But anything that's below a sub k, so any value that's below a sub k, we can't remove, right? So this should be very obvious. Because there's no way it's not going to be there. There's absolutely just no way. Yeah. Dude, this is like, I need to explain this properly because, like, this is low-key the heart of the solution. So we've shown that we can remove all instances of the max. And basically, that's it. That's equivalent to just saying remove all x greater than a sub k. That's equivalent. We know that we can't necessarily remove all. We can remove some a sub k's, but we don't know when we can. So it's just wipe off everything that we can for sure remove, which is everything that's greater than a sub k. Yeah, that's good. Once we have those values, the question is, what elements can we delete? But it should be obvious that. Oh, okay, I'm dumb. So, like, okay, any value. So let's say this is like a sub k, right? So obviously, like, let's say this is the sort of position, and maybe this is a few more a sub k's, but then I have an element like here. Like, in order for you to like be removed, you must have k minus one smaller elements, right? And obviously, any value that's under a sub k will not have k minus one smaller elements, for the very obvious reason that it's simply like if this is where a sub k is, you could have some a sub k here too, and a sub k same value here. So if the value here is x, you could also have some x here. But anything that's underneath this, right, will clearly not have k minus one smaller values. So it's kind of bottlenecked, right? So basically, we know that we can't remove, we can only remove a sub k. So that's like the huge observation. And so if we're checking this as a palindrome, and if these ends don't agree, then I would just remove two, right? And then I would remove this pointer in here. And if the ends don't agree, I'll just remove two and move this pointer, and then we have a palindrome. So that's basically what we'll simulate. But we know that we can only remove this element as long as like we had as long as k minus one elements are left. Because there always must be at least k minus one elements left in the array. Okay, so that's good. So yeah, first thing we'll do is we'll sort it, and then we'll notice that anything under k smallest can be added, right? Everything else at greater than a sub k, just get out of here. Like we can remove all instances and we'll still be fine. Like that's a good thing to do because we proved that. Okay. So once that's gone, then we can just check if it's a palindrome. And basically, if the ends don't agree, then we have to remove the max. But if one of them is not the max that we have to remove, then it's impossible, right? Otherwise, we say like count and we have to remove the max. But like the amount of elements that we have left must be at least k minus one, and that's what this thing does. It's a solution. This is like funny Java. Like this prints out false, by the way. But yeah, that's the problem. So general review of the problem is you first have to make this observation that removing all instances of a number still keeps it a palindrome. And so just start with a max and just remove all instances there. And then just realize that you always need at least k minus one elements. So you might worry that removing all instances. So just think about the number sort. You might worry that removing all elements instances will take you underneath k minus one. But obviously, if you remove everything that's greater than a sub k, like you'll be fine. Um, and then you realize that another way to reword the same condition is like, can you form a subarray such that k minus one elements are smaller? Anything below a sub k obviously can't be removed, so those are fixed. And then just use the 2 pointers to check if it's a palindrome, and the solution's kind of clear. So yeah, this is like a clean way to solve the problem. Yeah. All right. Nice.